Good afternoon, my dear students. Today we are going to discuss design of FIR filters. In the design of FIR filters, we have different methods. Among those methods, today we are going to discuss Fourier method, which is also called as the Fourier series method. So, in order to design a FIR filter, in order to design these FIR filters, we are going to use either Fourier series method or the digital filters using window techniques. So with the help of these two and one more, the frequency sampling technique, with the help of these three techniques we are going to design FIR filters. First of all, let us discuss about this Fourier series method. Fourier series method. Let us put heading. That is a Fourier series method of designing FIR filters. Let us put heading. In the syllabus, it is given Fourier method, which is also called as a Fourier series method. So that is the reason. Let us put heading the Fourier series. The Fourier series method of Fourier series method of designing FIR filters. Okay, so here whatever the method it is, we are going to derive the expression for the frequency response. That is, here the frequency, the filter frequency response is represented by h of e power j omega. Why? Because we know that frequency response is related to the frequency domain. So in the frequency domain, we are going to take e power j omega. That is the frequency response, which is represented by whatever the filter it is. In general, the frequency response of filter is represented by h of e power j omega. Okay, the frequency response h of e power j omega of a system is periodic in 2 pi. Is periodic. We know that a Fourier series is used for periodic sequences. Okay, so here the frequency response h of e power j omega of a system is periodic in 2 pi. Periodic in 2 pi. From the Fourier, I'm going to continue here. Okay, from the Fourier series analysis, any periodic function can be expressed. Any periodic function can be expressed as a linear combination of as a linear combination of exponential. As a linear combination of exponential. Complex exponentials. As a linear combination of complex exponentials. Therefore, the desired frequency response of a filter can be expressed as the desired. We know that a frequency response is represented by h of e power j omega. Desired frequency response of filter is represented by h suffix d of e power j omega. That is the desired frequency response of the desired frequency response of filter the desired frequency response of an FIR filter. An FIR filter can be represented by the Fourier series. Therefore, which is represented by ht of e power j omega is equal to summation n is equal to minus infinity to infinity. It is a frequency response, and a small hd that is represented by impulse response. That is desired impulse response hd of n into e power minus j omega n. Okay, where hd of n is a Fourier series coefficients, where h suffix d of n or simply you can write it as where the Fourier series coefficients are where the Fourier coefficients hd of n are the desired impulse response. We know that an impulse response is represented by h of n, and the desired impulse response is represented by h suffix d of n. As we know that to get an output from a filter, how we will get an output? When we consider x of n as an input, and by convolving that x of n with impulse response, we will get output y of n. In similar way, here also, to get the impulse response of this FIR filter, that is that impulse response is represented is also called as a Fourier series of that impulse response h of n, which is represented by desired filter. When we consider the desired filter impulse response hd of n, whose Fourier series is represented by Fourier series of that or the frequency response of that desired filter, that is capital H suffix small d power e power j omega. Okay, wait a minute. Okay, so desired impulse response. desired impulse response of the filter, desired impulse response of the filter. So which is represented by small h suffix d of n, which is equal to 1 by 2 pi. As we have discussed starting of this, the frequency response h of e power j omega of a system is periodic in 2 pi. So according to that, the integration limits minus pi to plus pi. The overall duration 2 pi, which is equal desired filter frequency response h of e power j omega into e to the power of j omega n. Inverse Fourier transform. If we consider this one as a Fourier transform, as we have started, it is a Fourier series. So it is a Fourier series expression for the frequency response. It is inverse Fourier series. So to apply the inverse Fourier series to the frequency response of an FIR filter, we will get a desired impulse response. Okay. Consider this one is equation number 1 and this one is equation number 2. Now let us write down the jet transform of this filter. Here we know that jet transform is represented by h of jet, which is equal to summation n is equal to minus infinity to infinity, this one. So whatever we have, the desired impulse response of the filter by applying jet transform to this, which is represented by hd of n into z power minus n. So consider it is the representation of jet transform of desired impulse response. Let us consider this one is equation number 3. So from this equation number 3, it represents a non-causal. We know that. So when a system is said to be causal, whose duration here, when a system output is depends, so based on the depending of the system output, we are going to define a causal system. In similar way here also, in this output is depends on the future inputs also, but in causal system the output of a system is depends on present and past values of input. Okay, so according to that, which represent this equation 3 represent non-causal digital filter. It represents a non-causal digital filter. A non-causal digital filter of a non-causal digital filter of a infinite duration. To get in a FIR filter, to get an FIR filter, function. What function it is? Transfer function. To get an FIR filter transfer function, how we are going to represent that transfer function? That is capital H. Okay, to get an FIR filter transfer function, the series can be truncated by actually the Fourier series is periodic, so which is truncated by assigning h of n is equal the desired filter frequency response hd of n for small n value lies between minus n minus 1 by 2 to plus n minus 1 by 2, that is capital N, where the capital N that indicates the length of the filter. Okay, so which is also represented magnitude of n is equal, n is less than or is equal, which is magnitude of n is less than or is equal to capital N minus 1 by 2, and which is equal to 0 otherwise. Then let us write down. Already we have mentioned here the filter to get an FIR filter transfer function, that is capital H of Z is equal summation. Now here instead of taking the summation, in the summation initially equation 3 small n range minus infinity infinity, but here to get an FIR filter we are going to truncate the series. The series can be truncated by assigning the limits, that is a small n value lies between minus of capital N minus 1 by 2 to plus n minus 1 by 2 into hd of n into z power minus n, hd of n into z to the power of minus n. Okay, so now let us expand this summation term. So let us substitute at which we have the n. So at that place initially let us substitute minus of capital N minus 1 by 2. That is how we are going to mention that. That is mentioned like this. Let us take h of, is it hd of n or h of n? H of n is equal to hd of n. So instead of writing hd of n, we can also write it as when the small n value less than or is equal to at which we have the hd of n, we can also write it as h of n. Okay, let us write down that step according to this. Okay, so small n value minus of capital N minus 1 by 2 to capital N minus 1 by 2 into h of n into z to the power of minus n. Okay, so let us expand that summation. By expanding that summation term, what we will get? H of minus h of minus n minus 1 by 2 minus n minus 1 by 2. So here instead of substituting minus n minus 1 by 2, initially let us substitute positive values. After completion of that, substitute the negative value. So here first of all let us substitute the positive values, that is let us substitute n value is capital N minus 1 by 2. So by substituting that, what we will get? Small h of capital N minus 1 by 2 into z power capital N minus 1 by 2. Already we have the minus, so at which we have the small n, we are going to substitute in place of that n, we are going to substitute capital N minus 1 by 2 plus and so on plus and so on plus h of 1 into So here at which we have the n, in place of that we are going to substitute 1 small n, at which we have the small n. So okay, h of 1 into z to the power of minus 1 plus h of 0 into z to the power of 0 means f of 0 value 1. Okay, plus now let us substitute the negative values. H of minus 1, in place of minus 1 what we will get, z to the power of minus plus 1 plus h of minus 2 into z to the power of minus plus plus and 1 to h of minus of n minus 1 by 2 into z to the power of plus n minus 1 by 2. Okay, now let us simplify that expression. So in this expression we have the term that is h of 0. Let us write down that h of 0 term first and plus summation. Here we are going to take n is equal to 1 to n range, 1 to n by 2 minus 1. So this is also not n by 2 minus 1, it is n minus 1 by 2, n minus 1 by 2 for whole n minus 1 by 2 we have. Okay, so the range is a small n value 1 to capital N minus 1 by 2. Okay, so according to this expression, how we are going to mention that? That is mentioned like this: h of n into z to the power of minus n plus h of minus n into z to the power of plus n. For a symmetric h of n is equal to h of minus n. Let us consider the impulse response as symmetrical. For a symmetrical impulse response, h of n is equal to h of minus n. Okay, so let us write down that according to that symmetrical impulse response. Consider the impulse response is symmetrical, then the above expression can be modified it as h of 0 into summation small n is equal to 1 to n minus 1 by 2 into h of n into z to the power of minus n plus h of n into z to the power of plus n. Let us take h of n as a common in that expression. By taking h of n common from that expression, what we will get? N is equal to 1 to n minus 1 by 2 by taking h of n common, what we will get? Z power n plus z power minus n. Okay, so the above transfer, so whatever we got the transfer function after applying Z transform to the desired impulse response of a filter, it is not realizable. It is not realizable. The above transfer function, it is a transfer function, it is not realizable. So to get the realizable to make the realizable transfer function of a FIR filter, we are going to multiply with e power minus of n minus 1 by 2. First of all, the above transfer function is not realizable. Is not realizable. So realizability, so to make realizability can be brought by multiplying the above expression with, consider that expression can be represented by equation number 4. Multiplying equation 4 with e to the power of minus of n minus 1 by 2. Okay, now let us write down that realizability of the transfer function. The realizable transfer function can be represented by h dash of z, which is equal to e to the power of minus of capital N minus 1 by 2 into h of 0 plus summation n is equal to 1 to n minus 1 by 2 into h of n of z power n plus z power minus n. So this one is a frequency response of an FIR filter by using Fourier series method. Finally, our main objective is to get the frequency response of a filter. So it is a transfer function. So by using of this transfer function, we will get the frequency response. Already we have mentioned here this equation 4, whatever we got the transfer function, that is not a realizable one. So to brought as a realizability of a transfer function, we are going to multiply with e to the power of minus of n minus 1 by 2. So it is a transfer function that is a realizable transfer function, of FIR filter, realizable transfer function of FIR filter. So initially what we have taken, let us recall once again. What we have taken, initially we have taken a desired frequency response. From that desired frequency response, we have taken a desired impulse response of a filter, and by applying a Z transform to that desired impulse response, we will get h of z, where the h of z is also called as a transfer function or the system function. So by applying limits, why? Because we are going to truncate the Fourier series. Why? Because actually the Fourier series is a periodic. According from the Fourier series analysis, any periodic function can be expressed in terms of linear combination of complex exponentials, as we have mentioned here, linear combination of complex exponentials here. Okay, so finally what we got the transfer function. It is a transfer function. What type of transfer function it is? It is a realizable transfer function. Okay, thank you.